Okay, so this is example 1. The choice set, I mean the set of alternatives, are coming from r plus square. All right, so basically they are non-negative vectors of reals. So these are the alternatives. There are infinitely many of them. All right, it's not finite set. So, well, sometimes if the set is not finite, things may be complicated because it's a bit more abstract. But you shouldn't really worry about it if you know how to sort of formally make a logical deduction. All right, so this is our choice set. You call it x if you want to. So it's basically a vector, something like xy. All right. Well, I'm going to define the following. So define the binary relation on x as follows. A bundle, I'm going to call them bundle rather than alternative. xy is at least as good as uv. uv is another bundle, all right? They both are in r square plus. So xy bundle is at least as good as the uv bundle if and only if and only if. So this is a definition, so therefore even if I said if, it means if and only if. If and only if xy vector is greater than or equal to uv. Okay? So here, that's it. I mean, that's the definition of this binary relation. This is a well-defined binary relation. And here, however, I want you to be careful about the notation. So this is, this is at least as good as sign, all right? It looks like greater than or equal to, but it's not. And the reason is, different typing software have different symbols. If you use LaTeX, I don't know what it looks like in Word, for example. But, there is this, this is not equal to sign, all right? So it's sort of, a wavy thing. So this is greater than or equal to, all right? It's like, the greater than or equal to that we use in real numbers. But this is at least as good as, so be careful. At least as good as. The reason why we use a different symbol is because we don't want to use greater than or equal to sign, all right? Because the greater than or equal to sign is usually defined on reals, real numbers or real vectors, but they're defined on reals. At least as good as, however, can be defined on anything, right? My choice set, my alternative set of alternatives, can be any set, like, I don't know, cars, available partners, whatever. So xy's do not really have to be numbers. So in that sense, and on top of that, I don't want to say greater than or equal to. I just want to say at least as good as. So for this purpose, I basically use a different symbol, and it happens to be this one. So here, however, it's sort of related, right? Greater than or equal to and at least as good as, because, I say they're equivalent to. If you need, let's remember you have to, if you don't remember, what it means by, a vector is greater than or equal to another vector. So here is how I can define it, maybe. So xy is greater than or equal to uv if and only if x is greater than or equal to u and y is greater than or equal to v. All right, so this is how we basically define greater than or equal to sign when it becomes a vectors of reals, as simple as this. Okay? But we don't make any such definition here, right? I can't say xy is at least as good as uv if and only if x is at least as good as u and y is at least as good. No, all right? Be careful about this, because this is not greater than is or equal to. However, I say a vector is at least as good as another vector if it is actually sort of greater than or equal to the other one. All right. So my first question would be, is this binary relation a preference relation? Is it, one, reflexive? Why am I using blue? Don't know. One, is it reflexive? 2, is it complete? Maybe the most important one. And the 3, is it transitive? Okay, so remember the definitions of these axioms or the axioms. And then, of course, 5, we can ask, so we can define a choice behavior by using this preference relation and then ask, does this choice behavior satisfy condition alpha, for example. I will come to this later. I don't know why it is 5. It should be 4. But let's first tackle these 3 questions: reflexivity, completeness, and transitivity. All right? So, is it reflexive? Well, what does reflexive binary relation means? A binary relation, I assume you already know the definition, but let me just repeat it. A binary relation is reflexive if, actually that means if and only if, for any, in this world, my binary relation is r plus square, so I'm gonna take a vector, all right? I'm not making a general definition here. So for any vector xy, xy should be at least as good as xy itself, right? So that's the definition of a binary relation being reflexive. That's it. Well, is it really the case? Well, this is sort of a direct proof. How do I know, or how do I make sure that this is true? Well, remember, it's if and only if this is true. So let's see. So I have xy, some vector, by the way. I don't know what it is. That could be, all I know is that they're not negative, right? So this is just a vector. What I know is that any vector, we know that any xy in R plus square, xy is at least, greater than or equal to itself, right? I mean, it is equal to itself, but, you know, what does equal to mean? Equal to means the first guy greater than or equal to the second, and the second is greater than or equal to the first, so therefore they're equal. So nevertheless, I don't need, so it's like if and only if Q, if and only if P, P if and only if Q is, remember, P implies Q and Q implies P, kind of, right? So here there's no implication, but it's like one is greater than or equal to the second one, so I use just one side of it. So we know that, right? Every vector is greater than or equal to itself. So therefore, by definition of this preference relation, right? By definition of this preference relation, this vector is at least as good as itself. And this is true for any xy. So then that's it. We basically proved that this binary relation is reflexive. Okay? Good. By the way, in a question like this, is it reflexive? Well, you either, if you think it is reflexive or complete or transitive, you either provide the proof of it, or if you think it is not reflexive or complete or transitive, you give a counterexample. Does anybody know what counterexample mean? Anybody? Or anybody heard of it? Okay. Are you there, by the way? I don't hear anybody. Okay, yeah, I just wanted to make sure that you guys are there. All right, so counterexample is not a proof method, all right? I'm just showing that an argument is false by sort of representing one case where the argument fails to hold. That's it, all right? So it's a counterexample means I am giving an example for the counter argument or the negation of the argument. So if you want to show that something is complete, but in fact you believe it's not complete, so what you do, well, the negation of completeness is, well, it's not complete. So therefore I am showing one case, one example where this completeness idea fails to hold. So that example is called counterexample. Because here I proved reflexivity, I mean, I can't find any counterexample, right? What does that mean? it would mean you need to find a vector xy, a vector of reals, where it's not greater than or equal to itself. But trust me, you can't find such a real vector. All right, so the next is then completeness. Is this binary relation complete? What do you think? Anybody? Do you have any hunch? Okay, you guys are quiet today. Fine. A binary relation is complete if for any vectors in my set of alternatives, either xy, oops, I'm sorry. For any two, right? It should be for any xy uv in R square plus, such that either xy at least as good as uv or uv at least as good as xy. By the way, what does that mean? That means either this is true or this is true, right? This is P or Q statement. So either this is true or this is true. We usually don't put blah blah is true or blah blah is true, because this is read as either this or this means either this is true or this is true. So, well, obviously it's a matter of experience, right? If you have never sort of thought about this before, you probably don't know whether you should start searching for a counterexample or searching for a proof, right? How should I start? Well, it's a matter of choice. I would recommend you to first try to find counterexample. I mean, try to show that for some examples, for some x, y, and uv, this doesn't hold. Try to come up with an example. So for any argument, try to disprove them first. All right, so try to come up with counterexamples. The reason is, well, when you work on finding counterexamples, actually you're going to learn a lot. You learn a lot how things work in this environment. And so if you can't find, after some search, few attempts, if you can't find a counterexample, that actually may mean that the statement is true. And so you may start proving the argument. All right? And when you sort of try to prove it, you may stuck at some point. And, the proof, the logical deductions you had previously may actually lead to another sort of example that you did not consider before, and so that might be your counterexample. All right, so you basically go back and forth between proving the argument, trying to find a counterexample. So there's no one correct way. However, because our time is limited, what I'm going to do here is, start with finding a counterexample. So remember the definition of the binary relation back of your mind is like, it actually means the vector is greater than or equal to. So is this the vectors being greater than or equal to another one? Is it a complete relation, right? I mean, you may not know it, but for example, can you compare a vector 1, 2 and 2, 1? Which one is bigger, greater than or equal to? Can I say 1, 2 is greater than or equal to 2, 1? Is it true? Or can I say, 2, 1 is greater than or equal to 1, 2. Is this true? Well, remember the definition of a vector being greater than or equal to another one. It means the first components should be greater than or equal to. Well, it fails because 1 is less than 2. So this is not true. All right, so this is false, clearly. All right, what about this? 2 is greater than or equal to 1. Yes, good. 1 is greater than, no, it is not. So therefore, this vector is not greater than or equal to 1, 2. So you know what? This one is also false. So you know what? I found an example for xy 1, 2 and uv is 2, 1, which are an element of R square plus, right? So they are in the element of, in my set of alternatives. And neither this nor this is true. So therefore, this binary relation, I'm sorry, by the way, remember, if this is false, because by the definition, if and only if, so this must be false as well, right? And again, because this is false, because the definition is an if and only if statement, this must be false as well. So therefore, I found an example where both of these are false. So that means I actually found a counterexample, meaning, one, this relationship, this binary relation, is not complete, right? So it's not complete. And you know what? Here's my example. Well, is this the only example? Well, no. I mean, you can find millions of examples. Instead of 1, 2, make it 2, 5, 5, 2, right? It doesn't have to be sort of the mirror image of the same thing. It could be, for example, 1, 3, and then, for example, 2, 5. So again, I'm sorry, 2, 5 is greater than this guy. So it should be something like, so 1 is bigger than the other is smaller, all right? So 2 is bigger than 1 here. So therefore, this number should be less than 3. For example, 0. All right. So whenever you find such an example, there are millions of them. You cannot really compare them according to this sign, greater than or equal to. So that means equivalently, I cannot compare them according to this binary relation. And hence, this binary relation is not complete.